Right now, as you watch this, you exist in multiple places at once. Your atoms are spinning in opposite directions simultaneously. You're both here and not here until someone checks. This isn't philosophy, this is quantum physics, and it's breaking every rule we thought we knew about reality. For over a century, physicists have been trying to make sense of the quantum world. The more they discover, the stranger it gets. Particles that communicate faster than light, objects that exist in two places at once, reality that doesn't exist until you observe it. Today, we're diving into the heart of quantum mechanics. No complex math, no jargon, just the mind-bending truth about how the universe actually works at its smallest scale. By the end of this video, you'll understand why Einstein called quantum physics spooky, why it challenges everything we think we know, and why scientists still can't explain what it all means. Let's start with the basics. Quantum physics is the science of the very small. Atoms, electrons, photons, the building blocks of everything. At this scale, the rules change. Completely. In our everyday world, things are predictable. Drop a ball, it falls. Turn on a light, photons travel in straight lines. Cause and effect. Simple. But zoom into the quantum realm, and predictability disappears. Particles don't have definite positions. They exist in what physicists call superposition. Not here or there. Both, simultaneously. Think about that. An electron isn't at point A or point B. It's at both points at the same time. Only when you measure it, when you look, does it choose a location. This isn't a limitation of our tools. This is how reality works. The particle genuinely exists in multiple states until observation forces it to pick one. Niels Bohr, one of the founders of quantum mechanics, said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." He was right. The double-slit experiment proves this. It's been called the most beautiful experiment in physics, and the most disturbing. Here's how it works. But before we get to that, here's the part that makes physicists uncomfortable. Take a barrier with two slits. Fire electrons through it one at a time. Behind the barrier, place a detector screen. If electrons are particles, little balls, you'd expect two bands on the screen, one behind each slit. That's not what happens. Instead, you get an interference pattern, multiple bands, the signature of waves, not particles. Waves from both slits overlap, creating peaks and troughs. Constructive and destructive interference. Classic wave behavior. But here's the kicker. You're firing electrons one at a time. One single electron. It can't go through both slits, right? Wrong. Each electron somehow goes through both slits simultaneously. It interferes with itself, acts like a wave spread across space, until you watch it. Place a detector at the slits to see which one the electron passes through. The moment you observe, the interference pattern vanishes. Two bands appear. The electron stops acting like a wave. It becomes a particle again. Your observation changed reality. Not because you bumped into the electron, not because your equipment interfered, but because the act of measurement itself collapses the wave of possibilities into a single outcome. Werner Heisenberg, another quantum pioneer, put it bluntly. The atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities, rather than one of things or facts. Reality isn't real until you look at it. And this is where things get even stranger. Einstein hated quantum mechanics. He famously called it spooky action at a distance. He was talking about entanglement. When two particles interact, they can become entangled. Their properties link together. Measure one particle, and you instantly know something about the other, even if they're separated by millions of light years. Change the state of one, and the other responds. Instantly. Faster than light. Einstein thought this proved quantum mechanics was incomplete. Information can't travel faster than light. It's a fundamental rule of relativity. But experiments have confirmed entanglement again and again. It's real. In 2022, The Nobel Prize in Physics went to 3 scientists who proved entanglement beyond doubt. Here's the mind-bending part. The entangled particles don't have defined states until you measure one of them. The moment you do, both particles decide their states simultaneously. It's not that information travels between them, it's that they share a single quantum state, no matter the distance. John Bell, who created the theorem that tests entanglement, said, "The quantum world is not built out of things in space, it's built out of correlations. Space doesn't separate entangled particles. They're connected at a level deeper than physical distance." But wait, if that breaks your brain, this next part will shatter it completely. Quantum mechanics works perfectly. It's the most accurate scientific theory ever created. Every smartphone, every computer chip, every laser, every MRI machine, built on quantum principles. But we don't know what it means. Physicists call this the measurement problem. Before measurement, a particle exists in superposition, all possible states at once. The math describes this perfectly with something called a wave function. Then you measure. The wave function collapses. One outcome emerges. But why? What counts as a measurement? Does it require a conscious observer? Or does any interaction with the environment count? Nobody knows. There are multiple interpretations, none proven. The Copenhagen interpretation says, stop asking. Measurement collapses the wave function. That's just how it is. The many worlds interpretation says, every possible outcome happens. The universe splits into parallel branches. You just experience one branch. The pilot wave theory says, particles have definite positions all along. They're guided by a hidden wave we can't detect. Physicist Richard Feynman, who won the Nobel Prize for his work in quantum mechanics, admitted, "I think I can safely say that nobody understands quantum mechanics. Even the experts are confused. So why does any of this matter? Because quantum mechanics reveals something profound about reality itself. Reality isn't a stage where events unfold. It's not a collection of objects with fixed properties. Reality is a web of possibilities, potentials that crystallize into actuality only when observed. This challenges determinism, the idea that the future is predetermined by the past. In the quantum world, randomness is fundamental, not just uncertainty because we don't know, but genuine randomness built into the fabric of existence. It challenges materialism, the idea that reality is made of solid stuff. Particles aren't tiny billiard balls, they're excitations in quantum fields, probability clouds, mathematical abstractions. It even challenges the separation between observer and observed. The act of measurement becomes part of the system. You can't study reality without affecting it. Quantum physicist John Wheeler proposed a radical idea. The universe is participatory. Observation doesn't just reveal reality, it helps create it. Wheeler said, "We are not only observers, we are participators. In some strange sense, this is a participatory universe." Whether that's true, we still don't know. What we do know is that quantum mechanics works, and it tells us reality is far stranger than we ever imagined. Let's recap what we've covered. Quantum physics governs the behavior of atoms and subatomic particles. At this scale, particles exist in superposition, multiple states simultaneously, until observed. The double-slit experiment shows that observation changes reality. Particles act like waves until you measure them. Quantum entanglement links particles across any distance. Measure one, and the other responds instantly. The measurement problem remains unsolved. We don't know why or how observation collapses possibilities into a single outcome. And all of this suggests reality isn't what we thought. It's not solid. It's not predetermined. It's a shimmering field of potentials waiting to be realized. If quantum physics breaking reality blows your mind, you're going to love what's coming next. In part 2, we're diving into quantum entanglement even deeper. How it challenges Einstein's theory of relativity, and why some physicists think it proves space itself doesn't exist. That video drops in 2 days. Hit subscribe so you don't miss it, and tell me in the comments, What part of quantum mechanics confuses you most? The observer effect, superposition, entanglement? Let's discuss it. Thanks for watching. This is Veritas Labs, where truth is tested.